Hello there! This lecture is going to teach you all about probability, specifically continuous probability for working with continuous scores. So if you remember, continuous scores are data that's truly numeric that can hold any value, fractions, or decimals, so not just fixed to whole numbers. The importance of this concept is that I'm going to show you how just with the mean standard deviation and the fact that you know you have a normal distribution, you can figure out what proportion of scores have a certain value, or in other words, the probability of randomly selecting a score with a certain value. And we're also going to look at the probability and proportions associated with sample means. So a lot of the things we're going to talk about in this lecture rely on concepts you've been introduced to in the past, specifically z-scores. So I'm going to give you a recap of z-scores and the things that apply to this particular lecture in case you've forgotten some of those concepts. We're going to also talk about the empirical rule, which is kind of the guidelines that tell us what specific probabilities and proportions apply to which specific values in a data set. Luckily, just knowing the probabilities in the empirical rule and your z-score, you can tell a whole lot of information about a data set without the raw data. And that's really the point of what we're doing here. Keep in mind that we're going to keep it basic in this lecture. You can find probabilities or proportions associated with any value or any value associated with probabilities and proportions. It goes both ways, but that'll be reserved for the Excel assignment. For this, we're just going to focus on kind of some basic properties of the empirical rule. We're not going to get into really specific exact values just yet. As we go through the lecture, it may seem a little bit lofty or confusing, but I promise you that at the end, we're going to do a ton of examples that'll help you really solidify your understanding of the concepts so that you'll be ready for the lecture quiz.
So again, we're going to start with a recap of terminology and the notation used for that terminology so that as we go through the examples, they will make sense and you won't feel lost. Again, we've covered these things, but I want to make sure that you understand them still. Also, we're going to get into what is a probability versus a proportion and how do you get a percent chance and what's the difference between percent chance and percentage of values. All those things are very similar, but there's minor differences that I want to cover. Then we're going to look at the empirical rule, which is that set of guidelines that tells you the probabilities and proportions associated with specific z-scores. Then we're going to apply that to just kind of give you an example of how it's used in finance. I know this isn't a finance class, but because the empirical rule and the normal distribution is used so much in finance when you're looking at investment portfolios, I couldn't resist introducing that concept to you here. Then we're going to do a ton of examples where we either find probabilities or proportions of scores, or we find scores associated with probabilities, and then we're going to do the same thing with means where we find probabilities or proportions associated with sample means and then flip the process to find sample means associated with probabilities and proportions. Now, right now, it probably doesn't make sense why we would do that, but in the examples, you'll see how there's very practical applications for understanding the empirical rule and being able to determine scores or means associated with probabilities and proportions. Before we can get to the fun, interesting probability stuff, we need to recap some terminology and notation that you've been introduced to in the past. So first of all, X represents a single score from a data set. So for instance, if you're measuring grades on a lecture quiz, each individual person's grade would be the X value for that individual person, their score. X bar is the sample mean. So if I took the lecture quiz, average for all students, added all those scores together, divided by the total number of students, that would be our sample mean, or X bar, which is just the average of all the scores in a sample. Lowercase n would be the sample size, and that's just how many scores would be in the sample. So if I was just looking at one lecture quiz, kind of like a sample of lecture quizzes, how many quizzes I looked at would be the lowercase n. Mu is the population mean. So if you look at, let's draw a little line here. Remember, for samples and populations, there's different notation. So we've got the sample mean here and then the population mean here. They're both the average. They're both taking all the scores, adding them together, dividing by the total number of scores, but X bar is for a sample and mu is for a population. Remember, a population is like everybody or everything that the researcher is interested in, but usually the researcher doesn't have access to everybody or everything, so they study them with a sample. Or if you're doing an intervention and you want to test it with a sample first and then compare it to the population, you could see where you'd have a sample and then the population would be everybody and the sample would be who got the intervention. So for instance, if I wanted to look at all the lecture quizzes that any of my students have ever taken, then the mean of all those quizzes would be the population mean, assuming that I was interested in all my students, not just you guys. Then we've got the population standard deviation. Notice that whenever we talk about a population, the notation is Greek. Whenever we talk about a sample, the notation is in just plain old English. So the population standard deviation just tells you how spread out the scores are in a population. Specifically, what is the average distance between all scores and the mean of all scores? Also, the population standard deviation would tell you if you just randomly selected, for instance, a quiz grade from every quiz grade I've ever had, what would be the expected difference between that quiz grade and the mean of all the quiz grades? It's kind of like the expected error if you're trying to make predictions. If I just randomly selected a lecture quiz grade and wanted to be like, okay, let's see like how well I think people are doing based on this one quiz grade, the standard deviation would tell you how far off my guess would be on average. The standard error is the typical difference between all possible sample means from a population and the population mean. So it's basically the standard deviation that applies to scores, and now the standard error applies to sample means. More practically, it's really for any given sample that you take from the population, how far off do you think that sample mean is going to be from the population mean? So if you're trying to get a representative sample of the population, if I was trying to take just a sample of maybe 6 students in the class to see how well I think everybody's doing on those lecture quizzes, the standard error would tell me how far off my prediction would probably be from the actual population mean. Now, the standard error is also useful if you're doing an intervention and you want to know how far away you would expect your mean and your sample to be from the population mean just due to chance. Even if your intervention had no effect, there's going to be some difference, and that some difference is your standard error. So when you do your z-score, you compare the actual difference between the group that you manipulated. For instance, you gave them training, you hope their performance improves. So you look at the performance in the sample that got the training versus the population performance mean, you find the difference. You don't know if that difference is substantial until you compare it to the difference you'd expect to see no matter what, even if the training had no effect, or in other words, you're comparing the actual difference to the standard error. So that's all recap from previous lectures, but I wanted to make sure that still made sense, and we still have some more to cover. So now let's recap z-scores, which are very relevant to the terms that I just showed you on the previous slide. So there's 2 different types of z-scores. One is the z-score for a single score, or x, and then the other is a z-score for a sample mean, or x bar. So when we're talking about a z-score for a single score, an x value, z tells you how many standard deviations above or below a single score is from the mean of all scores. So we're looking at the standard deviation. It tells you how far most scores are away from the mean, and the z-score says how far is your score away from the mean in terms of how far away most scores are from the mean. So it's a really nice way to compare one score to all the other scores in the data set in terms of the mean of all scores and then how spread out the distribution is. Remember, if you have a z-score that's positive, that means that that x value is above the mean, and if you have a z-score that's negative, that means that that x value is below the mean. Also remember that a z-score of 0 always represents the mean because a score that's equal to the mean is 0 standard deviations away from the mean because it's equal to the mean. Now looking at z-score for the mean, the sample mean, x bar. Now remember, when we talk about the sampling distribution, the distribution of all possible sample means that you could get from a population, our measure of spread is the standard error, not the standard deviation. So when we talk about z-scores for x bar, we don't say how many standard deviations, we say how many standard errors, because that's our measure of spread. That's how far away we think any given sample mean will be from the population mean just due to chance, or the typical difference between all sample means and the population mean. So now we say how many standard errors above or below a sample mean is from the mean of all possible sample means, or in other words, the population mean, because it's the same. And remember, when we look at the sampling distribution, we're looking at all possible sample means of the same sample size taken from the same population. So if, and I'll show you some examples of that here in a minute, but if we're looking at the z-score, remember, if it's a positive z-score here, that means that your sample mean is above the population mean. If you have a negative z-score, that means that your specific sample mean that you're interested in is below the population mean. So here's a visualization of two of those distributions, of a population distribution and a sampling distribution. Remember, the population distribution is all scores from the population, and the sampling distribution is every possible sample mean, in this case of 25 scores, that you could have gotten from this original population right here. Notice that the mean and the standard deviation are the same. Let's just, for a practical example, say that we're looking at, let's say that we're looking at grades on a technical report assignment. And let's just pretend for now that the overall grade possibility for that is like a 30 instead of a 20. So let's say we're looking at overall grades on the technical report assignments for every class I've ever taught in econ where we've used the same assignment. That would be represented here. So we would say that for the most part, people got a score of 20 with a standard deviation of 5. So really most scores were between 15 and 25, right? Remember, most scores fall within one standard deviation of the mean or between a z-score of -1 and +1. Now notice, and if you forgot how this works out, right? Check out these scores. Here's our z-scores across the top. This represents a score that's one standard deviation above the mean, or 1/5 above 20. Well, 20 plus 5 is 25. This z-score here represents a score that's 2 5s above 20. Well, 2 times 5 is 10. 20 plus 10 is 30. This represents a score that's 3 5s above 20. So 5 times 3 is 15, plus 20 is 35, and so on. You go to the left. This represents an X value, or in this case, a technical report score that's one standard deviation below the mean, or 1/5 below 20, 15, right? Then you just go down another 5, 10, another 5, 5, another 5 here, right? You're basically counting by standard deviations, up and then down as you increase or decrease your z-score by 1. So if we know in the population most people had a technical report grade between 15 and 25. Well, let's say that next semester or let's say that in the past, I never let students know where to go in their lectures or their Excel practice assignments to find the way to interpret and do the analyses that are required in the report. So I just gave them the requested analyses. I didn't tell them where to go to find out how to do it. But let's say this semester, I have 25 students and I start implementing that process where I give the students what Excel practice to look at and which lecture quizzes to look at to figure out how to do the analyses. And that distribution looks like this, where I say, okay, I gave 25 students this new useful resource. And I want to see how this sample mean in my class, and let's say the sample mean grade is now 22. I want to see how impressive that is compared to what I would expect to see just due to chance. And that's what this distribution represents, right? For any given possible 25 students that I would take, assuming that, they still represented the original population, that those additional resources had no effect, this is kind of the sample means I would expect to see just due to random chance. If I just took random 25 students from the population, I didn't make any changes to the class, this is what I would expect to see. So I would expect to see any given mean of 25 students to have a score between a 19 and a 21 within one standard error of the mean. Well, again, let's say that all of a sudden I say, okay, this time with these 25 students, I'm going to tell them where to look for in their previous assignments to figure out how to do the analyses in the technical report. And their mean grade is a 22. Well, I know that they have a 2-point higher mean than the population mean. So at first I'm excited, but I need to know how that compares to the difference I'd expect to see no matter what, my standard error. Well, this 22 is 2 times larger than the difference between 20 and 22, the 2-point difference, is 2 times larger than the difference I'd expect to see due to chance. My sample mean is right here, right? It's very unlikely, and we'll talk about how unlikely in a minute, to occur due to chance. So I'm feeling good, right? I'm like, oh, sweet. I think that giving them those resources improved their grades more than I would expect to see just due to random chance, even if those things had no effect. If I gave them those resources and I got a score of 21, not quite as exciting, right? Because that's within the realm of possibilities that I would get with any given random set of 25 students just due to chance, even if that additional information had no effect. So hopefully this is a review for you. If you're looking at this and you're still very confused, I would say maybe go back and review the sampling distributions lecture a little bit and just get up to speed before you continue on with this one, because we're going to be working in the sampling distribution and the population distribution quite a bit. But just remember, this is all the scores in the population, and the sampling distribution is all the possible sample means you could have gotten from the original population if you didn't do anything to the sample. Also, real quick, notice that the further away any given score is from the mean, the larger the absolute value of z is, right? It just keeps going up on both distributions, which means that the higher absolute value of z, the lower the frequency, right? Not very many scores have a z-score of -3 or +3, which also means that that score is more rare or has a lower probability. So the further you get out in these tails, the less probable, the less likely those scores are to occur due to random chance. And that's going to make more sense when we look at the empirical rule. So now I want to introduce you to some terms relative to proportions, probabilities, percent chance, and percentage of values. And again, all these things are very similar, but there's some minute differences that are important for you to understand before we move forward. You've probably been familiarized with these terms just in everyday life, but I want to make sure that they make sense. So as we move on, you'll understand what we're talking about. So the P represents proportion or probability. So when you're talking about this, you can speak in terms of what proportion or what relative frequency or how many overall relative to the rest of the group have a certain score or range of scores or a range of means. We'll say values just to make it apply to scores or means. Or you can say with the same number, the same p-value, okay, let's say that p equals 0.40 have a score above 80%. Well, then we have a 0.40 probability of randomly selecting somebody with a score over 80%. Those two things can be used interchangeably, and I'll show you some clear examples here in a minute of how those two things with the same value, you can interpret it different ways. How many overall, right, the relative frequency, and that also tells you how likely it is that if you randomly selected somebody, how likely that it would be that you'd get that value. Probabilities and proportions range from 0, never going to happen, nobody has that value, to 1, everybody has that value, and it's certain that if you randomly selected somebody, they would have that value. The percentage divided by 100 gives you P. So if you had 50%, then it would be a P of 0.5. What you can do, like if you have 50%, you just scoot the decimal 2 places to the left, right? So it starts at 50, you scoot it 1 place, now it's 5.0, scoot it 2 places, it's 0.50, P is 0.50 for 50%. So here's 2 examples of how you can explain the same value in terms of proportions or in terms of probability or likelihood. So the proportion of employees who made over $500 in commission is 0.30. You could also say, with the same exact information, the probability of randomly selecting an employee who made over $500 in commission is 0.30. See how you can explain it in terms of how many in the sample or the population versus how likely it would be to get somebody from that sample or population. Percentage is kind of the same, just a little bit of a different interpretation. For me, percentages are much easier to explain, but proportions are easier to use in mathematical equations. So a lot of times when I'm explaining things, I convert it into a percentage, because saying the proportion is blah, blah, blah is a lot more difficult than saying the percent chance or the percentage of. So just like the p-value, percentage is the relative frequency, which you learned about when we did frequency distribution tables. It's just the number of values with that, or the number of scores with that value divided by the total number of scores. And you can think about it in terms of percent chance, not probability, but now percent chance, how likely. But percent chance and probability to me are very, very similar. Now, just like P ranges from 0 to 1, Percentage ranges from 0% to 100%. So 0%, nobody in the sample has that value, or there's never going to be a sample mean with that value. Or you're never going to, if you randomly selected a score, it's not going to be that ever. To 100%, all the values have that value, all the scores have that value, and if you randomly selected, you're certain that you would get a score at that value because all the scores are the same. The way that you get a percentage from P is you just multiply it by 100. So if we had a P value of 0.30, you'd multiply it by 100 and you'd get 30%. Again, just like before where you were scooting the decimal 2 places to the left to get P, if you start with a P and you want to get to a percent, you scoot the decimal 2 places to the right. So if we have 0.30, scoot the decimal place 2 places to the right, so it's 30%. So using the same examples from before, we're converting it now into an easier for me to explain percentage type of way. 30% of employees made over $500 in commission. There's a 30% chance of randomly selecting an employee who made over $500 in commission. It's a lot easier for me to explain it that way than in the examples above. But see how they basically are saying the same thing. It's just really the way that you want to interpret it, the way that you want to state it. Now, although you can find the proportion, probability, percentage, or percent chance for any value or range of values in a data set, when we start talking about cumulative probabilities or percentages or percentiles, this always refers to specifically the proportion, probability, percentage, or percent chance of scores at or below a certain value. So not for any given range you want or score that you want. Percentages or percentiles or cumulative percentages always refer to the percentage of scores at or below a certain value. If you are at a certain percentile, that tells you how many values are less than or equal to yours. So for instance, if you have a baby, you go in and they measure their head circumference and they tell you your baby's at the 70th percentile. That means that 70% of babies have a head as big or smaller than your kids, and what's left, 30% of babies have a head that's bigger than your kids. Same thing with like weight, right? You go in, they say your baby's at the 20th percentile. Well, that means that 20% of kids are as small or smaller than your baby, and 80% of kids are bigger than your baby. Also, think about this way. If you're measured, and with these, it's not really clear with the baby example, it's not clear which one's better or worse. But if you're being measured on a variable where higher scores are better, you want to be at a high percentile, like IQ grades or commission, right? Because that means that most people are less than or equal to you, and very few people are above you if you have a high percentile. But if you're being measured on a variable where lower scores are better, you want to be at a low percentile. So if you're being measured on number of customer complaints or number of call-offs or your body mass index, if you're worried about fitness, you don't want to be at a high percentile. If you're looking at number of customer complaints, you want to be like the 10th percentile, where only 10% of people had fewer customer complaints than you and 90% had more than you because you're killing it and you're doing a good job. So just keep that in mind. Here's some examples back to what we looked at in the previous slide. So you could talk about somebody is at the 70th percentile if 70% of employees made 500 or less in commission. So if you made 500 or less, then you would be in the 70th percentile because 70% of employees made 500 or less in commission. You could also say there's a 70% chance of randomly selecting an employee who made 500 or less in commission, or in other words, there's a 70% chance of randomly selecting somebody in the 70th percentile or lower. And here you go. An employee who made $500 in commission is at the 70th percentile. Again, because 70% of employees made 500 or less, and only 30% of employees made more than 500. So if we look at this in a picture, right, you see the percentiles there. They range from 0 at the low end to 100 at the high end. So if you were at the 30th percentile or the 70th percentile right here, 30% is here, right? Because this whole normal curve represents 100%. It's kind of like a pie chart, really. And then what's left over here, 70%, right? So if your sales put you right here, 30% of employees made more than $500 in commission, and 70% of employees made $500 in commission or less. Notice these aren't X values or z-scores, they're percentiles. You won't see these numbers displayed like this again, but I just wanted to show it to you so you can visualize percentiles. Also notice that the mean is always in the middle of these distributions, and because in normal distributions, the mean equals the median equals the mode actually, but that's not as important. And remember, the median's the midpoint, the mean is the midpoint. So 50% of scores are above the mean, and 50% of scores are equal to or less than the mean. Let's say that you took an IQ test and you were in the 40th percentile. Would you be feeling pretty good about yourself or not? I mean, I guess it depends on your standards, but that means that 40% of test takers had an IQ score less than or equal to yours, but 60% of IQ test takers had an IQ score higher than yours. So you might not be feeling as great about yourself. If at the end of the semester you're in the 90th percentile for this class for final grades, you should be feeling like a rock star. Only 10% of students did better than you, and 90% of students did as well or worse than you. So just think about how those percentiles work. This is one of the things you can really apply in everyday life, because anytime you take an exam or you take your baby in for a well check, you're going to get these percentiles, and it's kind of nice to understand what they actually mean. And you're going to see in a minute how the empirical rule can inform these types of percentiles when you have a normal distribution, and all you need to know are the z-scores. Normal distributions have precise probabilities or percentages of values within specified z-scores. So we'll go into these in just a minute, but I want to give you a broad overview of kind of what is going on here before we look at the specific probabilities. You'll notice here, you'll see all those z-scores. Bam. So these precise probabilities or percentages that I'm going to show you are referred to as the empirical rule. The empirical rule allows you to determine specific probabilities or percentages associated with any score or sample mean in a normal distribution based on that score or sample mean's score. This is an especially useful application of z-scores because it allows you to evaluate the likelihood of scores or sample means and make predictions about the likelihood of specific outcomes without access to the raw data. All you need to compute z is the mean, standard deviation, and sample size if you're working with a sample. And all you need to know is the scores or sample means of interest. You don't need all the data to do what I'm going to show you how to do in this lecture, which is great because oftentimes you don't have access to all the data. So let's take a look at this empirical rule picture. First thing, which you've already been familiar with, is that most scores are within one standard deviation of the mean. Well, now, with the empirical rule, we don't just say most scores. We know that 68% of scores are within one standard deviation of the mean. Now, if we take 100% minus 68, we get 32. Split that up, and that tells you that 16% of scores are above one standard deviation from the mean, and 16% of scores are at or below one standard deviation below the mean. If you look at that, that pertains to a z-score of -1 and then a z-score of +1. So another way to say this, 68% of scores have a z-score between -1 and +1. 16% of scores have a z-score less than or equal to -1, and 16% of scores have a z-score above 1. Now we also, with the empirical rule, know that 95% of scores are within one standard deviation of the mean, or have a z-score between -2 and +2. So what does that leave? Well, it leaves 5% of scores, right? 5% divided into these two tails tells you that 2.5% of scores are above or at least 2 standard deviations above the mean, or at least 2 standard deviations below the mean. Or in other words, 2.5% of scores have a z-score of 2 or higher, higher than 2, or less than or equal to -2.
Whenever we talk about the less than, we include the equal to because the cumulative probabilities are involved in these calculations. So just kind of keep that in mind. It's not as important, but just to give you context of why I'm explaining things the way that I am. Also notice that this applies to the sampling distribution as well, but instead of saying, 1 standard deviation above the mean, we would say 1 standard error away. So 68% of sample means are within 1 standard error of the population mean. 95% of sample means are within 2 standard errors of the population mean. And only 2.5% of sample means would be more than 2 standard errors above the mean, and only 2.5% of sample means would be 2 or more standard errors below the mean. There you go. So these are going to be the probabilities that we're working with and the proportions, and all the examples that we do will produce z-scores or values that you can use with this. So this is really just a sketch of the probabilities associated with the z-scores displayed. But please keep this in mind. The probabilities of scores or sample means can range anywhere from a proportion or probability between 0 and 1 or percentage between 0 and 100%. And z-scores can be any value. And just the same with x values or means, it can be any value. But in this lecture, we're just going to focus on the probabilities in z-scores pictured here. If you were manually determining the probabilities or percentages associated with the range of scores or sample means, or if you were manually determining which scores or sample means were associated with specific probabilities or percentages, you would use something called the unit normal table. If you take more advanced classes in statistics, you'll be using the unit normal table. But in this class, we're just going to focus on using an Excel assignment to do those specific proportions or probabilities, and really just to determine those probabilities or percentages associated with any range of scores or sample means, or determining which scores or sample means are associated with specific probabilities or percentages. However, before you get to those Excel computations, it's important that you're able to visualize the values and probabilities or percentages and understand when and how to use them. So that's really the point of this lecture and why we're just going to stick to the percentages and proportions that you see here. We're not going to do it for every possibility. That's reserved for Excel. So the rest of this lecture is going to be focused on actually determining specific probabilities and proportions associated with values and vice versa. So if you're working with data that's roughly normally distributed, which means that if you're working with a population, you need to have scores that are normally distributed, which most population distributions are. Most things that are measured in the population, most people fall in the middle, and you've got extremes on either end, or most things, it's not people necessarily, most items that you measure have characteristics that are kind of similar. Most scores fall in the middle, and you've got extreme on either end of the distribution. But remember, when you're working with a sampling distribution, specifically when you're working with z-scores, it's always normal as long as you have at least 30 scores in your data set. So usually, this empirical rule works well in most situations. But if you're in a situation where you don't have normally distributed data, then the empirical rule is not going to be as useful to you because the probabilities and proportions won't be so accurate. So just keep that in mind. But for our purposes, we're assuming normality, so don't worry about like situations that I would throw at you where this wouldn't work, because it's always going to work for us. So with the empirical rule, you can determine what proportion or percentage of scores or sample means are within any given range of values without the raw data. All you need to be able to do is convert that score or sample mean into a z-score. So you need to know the population mean and the standard deviation, and then you would convert that z-score into the proportion or percentage. So the z-score is really like the bridge between raw values and proportions and percentages. Here's kind of the same thing if you're wanting to look at not just the proportion, the relative frequency, but the likelihood for changing the way we interpret p or percentage of randomly selecting a score or sample mean in a specific range. Then again, you would convert your score or your sample mean into a z-score and then use that z-score to determine the probability. Because you notice down here, these aren't x's or means, right? They're z-scores. So again, that z-score is the bridge between raw values and probabilities or proportions. But sometimes you may want to kind of flip it. You want to know what scores or sample means have a specific likelihood. So instead of starting with a range of scores and wanting to know the probability, you start with the probability and want to know what score is associated with that probability or percentile. So in that case, you would start with a p-value up here. You would identify what z-score is associated with that p-value, and then you would convert that into an x or a sample mean depending on the formula that you'd be using. So let's take a look at that. Flowchart style. If you're working with just scores, not sample means, and let's say that you want to figure out the probability associated with a score. First, you would convert x into z using this formula that you see right here, the z-score formula. You've seen that before. Then you'd take that z-score and you'd figure out the probability or percentage using the empirical rule. If you wanted to figure out a score associated with a probability, so you're going in the reverse direction, you start off by finding the probability based on the empirical rule, determining which z-score that pertains to, and then converting that z-score back into x using this formula. If we're talking about sample means, let's say you want to figure out the probability or proportion associated with a specific sample mean. Well, first, you would convert that sample mean into z using these formulas here. So remember, to figure out the z-score, you take the sample mean minus the population mean divided by the standard error. This is just a more fleshed out version of that formula, where I give you the formula for sample mean, and then I give you the formula for standard error right here. So you'd convert that mean into a z-score. Then you would go take that z-score, find it along here, and determine what proportion or percent is associated with it based on these values. Or you could go the other way around. If you want to figure out what sample mean pertains to a specific percentage or proportion, you would start with the proportions, figure out where that would be located in terms of z, and then convert that z-score back into a sample mean using this formula right here. Notice these are equivalent formulas. This version just breaks down the standard error for you instead of assuming you know how to calculate it here. So in the examples that we're going to do in a little bit, we're going to really break down this process. I'll demonstrate it for you. I'll show you how to use it. But before we get to that, I want to show you how to apply the empirical rule to finance if you're an investor and you have an investment portfolio. So any investment or investment portfolio has two aspects, risk and return. Investors look for the lowest possible risk for the highest possible return. But typically, more risk yields a better potential for return, but also a worse potential for loss. So the normal distribution quantifies these two aspects, risk and return, by the mean for returns and standard deviations for risk. So the mean represents the expected returns, and the standard deviation represents the expected risk associated with those investments. So the mean, or expected value, you can think about this in terms of finance as a particular share's price mean change. So we're looking at the mean change, could be 1.5% on a daily basis, meaning that on average it goes up by 1.5%. This mean or expected value that signifies return can be arrived at by calculating the average on a large enough data set containing historical daily price changes of that stock. So the higher the mean, the better the expected return. Now the standard deviation indicates the amount by which that percentage return deviates on average from the mean. So the higher the standard deviation, the riskier the investment, as it leads to more uncertainty. But again, oftentimes more risk leads to more reward. That's in a lot of arenas in life, not just investment. So for example, between 2008 and 2018, a moderate risk index fund portfolio, which is the IFA Index Portfolio 50, has a mean or average return rate per month of 0.5% with a standard deviation or a level of risk of 2.5%. You see those right here. So if we look at this, I've computed all the X values for the expected return any given month. Remember this formula here, so you'll see that for 0, right, that's going to be the mean automatically, the z-score of 0, so that 0.5 goes here. And then as we go up one z-score, we're increasing by one standard deviation, or 2.5%. As we go down, each z-score, -1, -2, -3, -4, that expected return goes down by our standard deviation of 2.5%. Notice that 2 times 2.5 plus 0.5 gives you that 5.5 right here. Just showing you how these numbers came to be, because that's going to be important later. So if we look at this, using the X-score formula, you can see that most months saw a return between -2 and 3%. Specifically, 68% of months saw a return between -2 and 3% within one standard deviation of the mean. Granted, we could say, well, 95% of months saw a return between -4.5 and 5.5. That's even more of a majority, but this is more of kind of a narrowly focused what we expect to see most of the time. A lot of the reason this is so high is because it also includes these values. So if we look at this, just using the probabilities provided here that always hold true for z-scores in a normal distribution, you can get a pretty good idea of how likely certain changes or certain ranges of return are. So again, the anticipated rate of return this month, if you want to go even broader, would be between -4.5 and 5.5. That's within, two standard deviations of the mean. But there's a 68% chance that you would get between -2 and 3%. Also notice, if you look at these proportions, there's a 2.5% chance of getting an investment below -4 or -4.5% or below, or 5.5% above. See that 2.5% right there. Also, if there's a 68% chance of getting between -2% and 3%, well, that leaves this remaining 16%. So there's a 16% chance of getting -2 or below, or 3% or above 3%. So showing you how these values are related to these values based on the z-scores and the x's for those z-scores. So let's look at another portfolio that has a different level of expected return and risk.
So now let's take a look at a very conservative or low risk portfolio. So, for example, between 2008 and 2018, a very conservative low-risk index fund portfolio, or the IFA Index Portfolio 10, this is actually based on real data, has a mean or average return rate per month of 1% with a standard deviation of 0.5%. So remember, the mean average return rate is your mean, and then the standard deviation is kind of that risk associated with it. So here's our x values here based on these z-scores and remembering this formula. So if we look here, the z-score of 0 pertains to the mean, which is 1%. And then as we increase z-scores, we increase by 0.5%. As we decrease one z-score sequentially, we decrease by 0.5%. So if we look at this, using the X-score formula, you can see that most months saw a return between between 0.5, not even negative, and 1.5%, or within one standard deviation of the mean. Notice that with the moderate risk portfolio before, the expected range for the rate of return was between -2 and +3%. So that portfolio was more risky. It could lead to bigger losses, but also had the potential to earn double the rate of return on investment, right? So there was if you divide 68% in half, there's a 34% chance that you're going to get between a 1% and a 1.5% increase here. But in the previous example, it was up to 3% of increase in your rate of return. So you got to think about that, right? More risk leads to the potential for more return, but also more losses. So if we look at these percentages and how they relate to what we see here, you can see that 95% chance that you would get a return between 0% and 2%, right? Within one standard deviation of the mean. Or there's a 2.5% chance that you would get a return of 0% or less, right? If we look here, or above 2%. I hope these examples are showing you how to use this table to make decisions and figure things out. 68% chance right here that you're going to be between 0.5% and 1.5%. And then finally, we're getting super colorful these days, 16% chance that you're going to have right here, right? Less than or equal to 0.5% or greater than 1.5%. So if you go back and you compare this distribution to the previous distribution, you'll see that this one's less risky, but it also has less potential to earn you money. So again, just using the probabilities provided here that always hold true for z-scores in the normal distribution, you can get a pretty good idea of how likely certain returns and rate of returns are. If you're curious about this, if this is interesting to you, you can go play with some data down here at this website, and you can look at different years and different portfolios, and it'll demonstrate the fact that typically the distribution of portfolio investments and rate of return is normally distributed. Most fall in the middle, and then you've got extremes on either end of the distribution. So now I'm going to throw a ton of examples at you that will allow you to apply all the concepts that you were just introduced to specific problems. These example problems will be really, really close to what you see on your lecture quiz, so make sure that you understand them before you jump into that. So for this first one, we're going to look at how to figure out probabilities of scores, and then also how to figure out scores associated with probabilities. So I'll show you how to follow this top path and then also how to follow this bottom path to arrive at specific answers. So go ahead and take a moment to read this example problem before I explain it. So let's go ahead and highlight some of the really important bits of information here. So I'll use yellow. So Provost Shields is considering a merit raise of $1,200 per year to any full-time faculty member who has overall course evaluations above 4.5. So this is our X, our value of interest, for above 4.5. Without access to the raw data, she needs to determine how many full-time faculty out of 200, this is our population mean, or sorry, population size, would qualify to see if there are sufficient funds to cover the raise. If the population of NSC faculty have normally distributed overall course evaluation ratings with a mean of 4.0, right, population of NSC faculty, here's their mean, that's a mu, and a standard deviation, population standard deviation of 0.25, what percentage and how many would qualify for the raise? So after we figure out the percentage, we're going to convert that into how many based on this population size up here. So the first thing that we need to do is figure out what our z-score is, right? We have to go from X to Z. See there at the top? Using the z-score formula. So let's do it. So if we look at this, Z equals, okay, X, the score of interest, the course evaluation ratings that she's interested in looking at, 4.5, minus the overall mean, our mu, of 4, divided by our standard deviation, which in this case is 0.25. Okay, so let's do our math. 4.5 minus 4 is 0.5, divided by 0.25, and we get a 2. For all of these examples, we're going to end up with the z-scores that you see down there in that pretty picture, just so that we can use those proportions. So if we think about where somebody with a course evaluation rating of 4.5 would fall, they would be right here, the z-score of 2. Well, I just kind of erased it with my blackness there. That's okay. So we'd have 2. And so if we think about it, what percentage would qualify for the merit raise? Well, to qualify for the merit raise, they have to have ratings above 4.5. So they need to be in this region right here. Well, what percentage is that? 2.5. So 2.5% would qualify. If you're still confused about where that number came from, restart this slide. Now, that's not the end of it though. How many would qualify, right? How many? Well, to do that, I'm going to use the p-value. The p-value, the percentage is more useful for explaining, but the p-value is more useful for determining how many. So remember, to get p from percent, you divide by 100. So if I take that 2.5, divide by 100, scoot the decimal places 2 places to the left to be able to take p times the population size, it would be 0.025 times my population size of 200. So 2.5% comports to a proportion of 0.025. Okay, so I multiply that. 0.025 times 200 is 5. So 5, we're just going to say full-time faculty would qualify. So now Dr. Shields could figure out if she has enough money in her budget, 5 times 1,200, to cover the raises. I think she will. Maybe she should make the standards a little lower, but that's just me. All right, so let's move on to another example. All right, go ahead and take a second to read through this example. So in this example, we're going to use this formula again. We're going to take x, convert it into z, and then use that z-score to determine the probability. So first, we're going to determine the probability or proportion. Then we'll be able to figure out how many students. Okay, let's break this down. I gave you some notation here. Not always going to do that, so make sure that you can identify which values are which just based on the explanation. So we've got our population mean GMAT scores here and our standard deviation. This is roughly close to what the values actually are in the real population. The GMAT is just kind of like the GRE for grad school or the SAT or ACT for college. It's kind of like the entrance exam that a lot of business students have to take to get into business programs in grad school. So overall, in the population, the majority or kind of the mean score is 560 with a standard deviation of 120. So most people have scores between, what would that be, 440 and 680 within one standard deviation of the mean. UNLV only examines applications for students with a GMAT above 440. So in this case, this is going to be our score of interest here, our X. What percentage of students would make the cut? So in other words, have a GMAT above 440, right? Not 440 or below. And if 250 students applied, how many applications would they expect to review? So we'll call this our lowercase n, or we could actually call it our population. No, we won't call it our population because our population is all test takers. So we'll go back and we'll say this is our X value. This is our lowercase n. Okay, so let's figure this out. We have to convert x into z first. There's no x values here. That's the whole point of standardizing your scores into z-scores so you can use these probabilities. So let's figure it out. So to figure out our z-score, our x of interest is 440 minus our population mean of 560 divided by our standard deviation of 120. 440 minus 560 is 120 divided by 120 equals a z-score of 1. So if we look at this table, this graph, somebody with, and actually I screwed up, this is negative. Look at this, negative, negative, which makes sense, right? Because 440 is below 560. So we've got a -1 right here. Somebody with a score of 440 would be there, and we want to know what percentage of students would make the cut, right? Would have this. Well, there's two ways that we could figure that out. We could simply say, all right, well, we know 16% of students would not make the cut, right? Because they're at or below 440. So all these students, sorry about your luck. We're not even going to look at your application. Your GMAT score is too low. So you could take 100 minus 16, and you could arrive at 84% would make it. Would make the cut. Or, if you want to be fancy, you could add 68% plus 16%, and you would still get 84%. Well, however you want to do it, right? Because here's that 68 here, and then all the way to the end with the 16%. So if we look at this, 84% of students would have their applications reviewed. So that's really useful for the explanation, right? 84 would make it. They'd have their applications reviewed, but P is more useful for determining how many. So when we take P times, remember, 250 applied, and we want to know how many of those 250 would be reviewed. So remember, to convert the percentage into a P, you divide by 100. You scoot the decimal place to the left, so 0.84 is P times those 250 students that applied, and you end up with 40. Now, if you do this math, you don't get a whole number. It's okay. Just round. It's totally fine. So 40, and so 40 would make the cut. Oh, wait. I'm silly. Hold on. That's how many would not make the cut. Get out of here. 0.84 times 250 is not 40, it's 210. There you go. So 210 would make it. That 40 is coming from how many would not make it, right? So to figure out how many would not make it, just kind of for kicks, you could take 250 minus the 210 that would make it. You get 40. Or you could take the 0.16 that would not make it, multiply it by 250, and you still get 40. Would not make it. Frown. That doesn't even look like a frown. Silly PowerPoint. There you go. But in this case, your answer would be 210, right? That's how many applications they would expect to review. And now, because I love examples, here's another example where we're going to convert an x value into a z-score and then use that z-score to figure out the probability or percentage based on the empirical rule. So go ahead and take a second to read this example problem. All right, so let's break this down with our notation so we can use our formulas. Kibbles and Bits sells large bags of dog food to warehouse clubs. They use an automatic filling process to fill the bags. Weights of the filled bags are approximately normally distributed with a mean of 55 pounds. This is our mu. That's the population mean of all the bags that are filled in the process. Standard deviation of 2.5 pounds. Standard deviation. The company knows that Costco warehouse managers randomly test the weight of one bag, right? That's why we're talking about X, because we're using a single score, per shipment to make sure they weighed over 52.5 pounds. This is our score of interest before they accept the shipment. How likely is it that a randomly selected bag will not weigh over 52.5 pounds? Or in other words, be 52.5 pounds or less, and the shipment will be rejected. So let's take a look at this. First, convert X to Z. Z equals our X in this case, which is 52.5, minus the overall mean of the population of bags, 55. See, since I'm a psychologist, I focus on business, but I focus on people. I want to throw some examples in here that weren't working with people. We were actually working with merchandise here. So 52.5 minus 55 divided by our standard deviation of 2.5 equals 52.5 minus 55 is negative 2.5 divided by 2.5, the standard deviation, and you get negative 1. So if you randomly selected a bag and it was 52.5 pounds exactly, that would put you right here, right? That's kind of the cutoff for shipment rejections. So if we're talking about how likely is it that a randomly selected bag will not weigh over 52 pounds, right? 52 point, it will not be here, that it will be here, there's a 16% chance of randomly selecting a bag that is 52.5 pounds or less because 16% of bags weigh 52.5 pounds or less. So again, there's a 16% chance of randomly selecting a bag that's 52.5 pounds or less because 16% of those bags are expected to be 52.5 pounds or less. So the final answer would be a 16% chance that the shipment would be rejected. It's probably not a very good likelihood. They need to lower that standard deviation, get more consistency. And that would be your final answer. So now let's take a look at an example where we flip this. We start off with a p or a percentage, in this case a percentage. We convert that into a z-score using the empirical rule, and then we use the x formula based on the z-score to figure out the score associated with that percentage. So take a minute to read this example, and then I'll go through it. All right, so let's break this down so we can use that beautiful formula. Provost Shields is considering paying for faculty development training for any full-time faculty member who has overall course evaluation ratings in the bottom 16%. So anybody who has evaluation that represents those with an evaluation, that or lower, 16% of people have that score or lower, 16th percentile. All right, so this is going to be kind of our P or our percentage. Without access to the raw data, she needs to determine what course evaluation ratings would warrant the training. If the population of, uppercase N, 200 NSC full-time faculty have a normally distributed overall course evaluation ratings, the mean of 4, there's your population mean, and a standard deviation of 0.25. What is the course evaluation rating at the 16th percentile? Which course evaluation ratings would warrant training? All right, so in this case, let's take a look. So if we go here, we would know that we're looking at the bottom 16%. So where is that in this beautiful empirical rule graph here? Well, this is the bottom 16%. That represents a z-score of -1, right? That's the cutoff for the bottom 16%. So if we follow from the right to the left in our little flow chart up there, going from P to Z, we know we're looking at a z-score that represents P equals bottom 16%. It's not 1, it's -1. That's our z-score. So now when we use that x formula and we're plugging in all our values, we're going to have -1 for z times our standard deviation of 0.25 plus our mean of 4. So this becomes -0.25 plus 4, which equals 3.75. So any full-time faculty member who has overall course evaluation ratings at or below 3.75 would be given paid faculty development training. We also know, based on the original problem, that 16% of faculty would be receiving this training. So Provost Shields should be prepared to fund P times N 0.16 times 200 equals 32 trainees. There you go. That wasn't necessarily part of the question, but it's a nice little follow-up to how many would have this or lower. 32, because we know that 16% of all faculty have a z-score of -1 or lower, or in other words, an evaluation rating of 3.75 or lower. And here comes one last example of figuring out a score associated with a specific probability. So take a look at another kibbles and bits problem, and then we'll go over it and break it down. All right, so let's break this down. Kibbles and Bits sells large bags of dog food to warehouse clubs. They use an automatic filling process to fill the bags. Weights of the filled bags are approximately normally distributed with a mean of 55 pounds. There's our mu again. And a standard deviation of 2.5 pounds. Standard deviation. The marketing team is pitching to Sam's Club, and the warehouse manager wanted to know the weight of the majority of bags with 95% confidence. So what is the weight range of the majority middle 95% of the bags? This time, we're going to end up with an X value range from a low end to a high end. Let's first start, though, by figuring out what z-scores pertain to those X values by using our empirical rule and the fact that we know we're looking at the middle 95%. Well, that's represented by this right here, and we know we're looking at these two z-scores. So for our low end, we have to figure out what x value corresponds to a z of -2. For our high end, we need to figure out what x value corresponds to a z of +2. Let's do it. So let's first start off x low end. Remember, low end, z equals -2. So we have -2 for z times standard deviation of 2.5 plus the mean of 55. Well, 2 times 2.5 is, or sorry, -2 times 2.5 is -5 plus 55 equals 50. Because -5 plus 55 is the same as saying 55 minus 5. There's our low end. X for the high end. When we have z equals +2, so we have +2 times standard deviation of 2.5 plus 55 equals +5 this time, plus 55, which equals 60. So the majority, middle 95% of bags, weigh between 50 to 60 pounds. So, for example, let's say that they produced 1,000 bags, right? Well, then P times the population size, really it'd be the sample size here. So if they produced 1,000 bags, then we would be able to say that 0.95, right, because that's the original percentage, times 1,000, or 950 bags, would be between 50 and 60 pounds. 50 to 60 is the original answer, but I always like to show you how to take it a step further to figure out the actual number of items that would meet that criteria. Now let's do 4 final example problems. I promised you a ton of examples, and again, these are going to help you a ton with your lecture quiz, so I hope that you're following along and maybe even trying them before I go over the answers, especially for this now that you've seen the process a few times. But now we're going to kind of change it up a little bit. Instead of looking at scores, we're looking at sample means. So instead of looking at a population distribution, we're talking about a sampling distribution. So the formulas for this are a little more complex because we have to convert that standard deviation into a standard error to figure out the z-scores and the x values. So we're going to figure out probabilities of sample means and also sample means associated with probabilities. So now you'll see that these examples involve samples, right, not just scores. So you'll see for this first one, we're going to use these formulas to take a mean and then figure out the probability associated with it. So go ahead and take a minute to read this example problem before we jump in, break it down, and make it happen. So this is an example where we're doing an intervention and we want to see how well it worked compared to how different we think our mean would be just due to chance, and taking that a step further, because you did that when you looked at the standard error in a previous lecture, but now we're going to figure out the exact probability that this result would have happened due to chance. Not just, oh, our z-score is large, so it must be good, but specifically, how likely is it that we would have got this mean no matter what, even if the training was garbage and it had no effect, so that you can make better decisions. So here we go. Let's break it down. NSC develops a new training program for faculty to help them provide better feedback on written assignments. Before requiring it for all faculty, we're going to do a pilot test with N equals 30 faculty. So they participate in the training to pilot test it. Over the summer, they complete the training. Then HR compares their feedback ratings. Hey, I gave you the symbols there. That's nice. From fall student evaluations to the typical mean feedback evaluation ratings for all semesters for all faculty. So there's our population values here. How likely is it that the trainees would have earned a mean of 4.4, there's our sample mean again, or higher just due to random chance, or higher is important, just due to random chance sampling error? Should the training be implemented for all faculty? So we're going to compare what we actually got to all the possibilities we could have gotten just due to chance, even if the training didn't work and the sample still represents the original population. So first, we need to convert our sample mean into a z-score. So before we can do that, we got to find the standard error. So our standard error is equal to the standard deviation divided by the square root of the sample size. So that standard deviation, it's spelled out for you right there. It's 0.55 divided by the square root of 30, how many trainees we had. This becomes 0.55. Square root of 30 is 5.478. I typically round to the thousandths place. Equals 0.1. That's our standard error. So just due to random chance, even if the training had no effect, I would expect my sample mean to be about 0.1 points higher or lower just due to random chance. So just due to random chance, I would expect to have a sample mean between 4.1 and 4.3, right? Adding and subtracting 0.1 to this original population mean. So in this example, a z-score of -1 would have a feedback evaluation rating of 4.1, and a z-score of +1 would have an evaluation rating of 4.3. So now I'm going to see how much better mine is compared to what I'd expect to see just due to chance using my z-score. And then we'll take that z-score and figure out the probability associated with it. So z equals your x bar, your sample mean, 4.4, minus your population mean, 4.2. I'm already feeling good because my sample mean is higher, so the training seems like it improved it, but how likely is it that we would have gotten that improvement no matter what? We're going to find out. 4.4 minus 4.2 divided by our standard error, not our standard deviation. We just found that's 0.1. So this gives us 0.2 divided by 0.1, and we get a pretty impressive z-score of 2. But we're not done yet, right? We don't just want to know the z-score. Right now, we know that the actual difference in performance is 2 times larger than the difference we would expect to see just due to chance. But how likely is it that the trainees would have earned a mean of 4.4 or higher just due to random sampling error? So let's take a look. Let's make it red. That 2 is right here. So this represents 2 or higher just due to chance, and that lands us on a 2.5%. So there's a 2.5% chance that we would have gotten a sample mean of 4.4 or higher if training did not work. So it's highly unlikely that we got that mean if training did not work. So that probably means it's likely we got that mean because training actually worked. The sample no longer represents the population, so it'd be very unlikely to randomly get a sample mean of 4.4 from a sample of 30 from this population. So 2.5%, it's a low p that you would get this due to chance. So you probably got this mean because the training, oh, that looks a mess, probably worked. So would you implement it? Yes. You're confident that the reason you got that higher mean is because of the training and not due to sampling error. Here comes another example where we're going to convert a sample mean into z to figure out a specific probability. Go ahead and take a minute to read this question before we jump into it. All right, so now we're going to take a sample to test our assumptions about what the filling machine is doing with these kibbles and bits. So we didn't really do an intervention. We're going to take a sample of what we already have to see if our expectations or our assumptions are accurate. So let's do it. Breaking this down, Kibbles and Bits sells large bags of dog food to warehouse clubs. They use an automatic filling process to fill the bags. In the past, weights of the filled bags have been approximately normally distributed with a mean of 55. Here's our population mean that we're going to test against, and a standard deviation, yet again, of 2.5. The quality control team has been receiving complaints about underfilled bags and wants to see if the machine is still functioning as it did in the past. So they randomly select our sample size, 36 bags from the most recent batch, and they find a mean weight, X bar, of 50 pounds. Is this a likely result if the machine is still functioning in the same way, or is this extreme? An extreme result that we would get if the machine was still working the same. So if we find out that we have a really large z-score, it's unlikely that we would have gotten that due to chance. It's likely then that we got it because those original population parameters are no longer the case. The machine no longer has a mean of 55 with a standard deviation of 2.5. So let's see what happens. All right. First things first, mean turns into a z-score using those lovely formulas provided. So we start off figuring out the standard error. Okay, so the standard error is equal to the standard deviation divided by the square root of the sample size. So in this case, our standard deviation is 2.5, and we're looking at 36 bags. All right, so 2.5 divided by square root of 36 is 6 equals 0.417. That's our standard error. Okay. Now we pop that into the z-score formula. Z equals our x value, or sorry, our x bar value, our mean, our actual mean from our sample, 50, minus what we think the population mean is based on the past, divided by how big of a difference we'd expect to see between the sample mean and population mean just due to chance if the machine is still working properly. So 50 minus 55 is negative 5. And negative 5 divided by 0.417 gives us a whopping negative 11.99. Good God, y'all. Not good. It's like off the charts bad, right? So negative 11.99 falls way below a z-score of 2, right? So basically, if we're looking at less than a 2.5% chance of getting this, we would need to have something in this realm right here, right? So if we had a z-score between negative 2 and positive 2, we would know that there is less than a 2.5% chance of getting this result if the machine was still working the same. Or there'd be a more than 2.5% chance, really. So it would not be extreme, right, if it fell here. Well, guess what? It's super extreme. It's way off the charts. It's way below a -4. So we know that it falls way less than a 2.5% chance of getting a sample of 36 bags, the mean of 50 pounds, if the machine is still working and results are just due to random chance. So results are not likely due to chance. They're due to the machine filling bags less than in the past. So if we look at this, should they be concerned about their machine? Yes. Very unlikely, almost impossible, really. If we did this in Excel, it'd be like a probability like 0.00000003 or something. Very unlikely to get a mean of 50 with 36 bags due to chance. Or in other words, if the machine was still working properly and differences were just due to random flukes. Time to fix your machine. So now let's flip our flow chart. Still working with sample means, but now we're starting off with a specific p-value, or in this case percentage. We're going to use the empirical rule to identify the z-score associated with it. Then we're going to convert that z-score into a sample mean using the sample mean formula. So go ahead and take a minute to read this problem and then we'll break it down. All right, so now the provost wants to kind of figure out how good of a sample mean do I need to get to be confident that training had an effect. So instead of actually taking the sample mean and figuring out how likely it would have been, we're kind of doing the opposite, where we're saying, okay, instead of computing the z-score for my mean to determine how likely it was to get due to chance, I'm just going to figure out what training mean I need to get to be confident that it wasn't due to chance. So let me show you how this would work. So we've got our parameters here. We've got our population and our population mean and standard deviation. And then before implementing it, so NSC is developing a new faculty development training program for full-time faculty with low evaluation ratings. There's the ratings in the population. And that's not for everyone, that's among everybody that has low evaluation ratings. So we're just looking at that population now. Before implementing it for all full-time faculty with low evaluation ratings, they want to test it in a randomly selected sample of 9, sample size, full-time faculty with low evaluation ratings. In order to implement the training for all who need it, Provost Shields requires that the sample of trainees have overall evaluation ratings after training that are high and have less than a 2.5% chance of occurring due to random sampling error. So we're looking right here. Any value, this would be here all the way to here. So what's the minimum overall evaluation rating in the sample that would convince Provost Shields to implement the training, right? It needs to be high, less than a 2.5% chance that we would get the mean just randomly from any given 9 full-time faculty, even if the training didn't work. Here we go. We have to figure out what z-score is associated with this probability first. So the z associated with 2.5% on the high end equals, right there, positive 2. Now, before we can use our beautiful little formula, we need our standard error. So standard error equals our standard deviation of 0.5 divided by the square root of our sample size of 9. This becomes 0.5 divided by 3, because 9 square rooted is 3, equals 0.167. So just due to random chance, even if the training had no effect, and we hadn't even given the training yet, we just randomly selected 9 full-time faculty with low evaluation ratings, we would expect that their sample mean would be within 0.167 points of 3. And in that case, 3 minus 1.67 would be here, and 3 plus 1.167 would be here. Okay, that's our error. Now let's figure out our z-score. Or sorry, We already know what our z-score is. It's 2. Let's figure out our x value. Here we go. So let's take the z-score at that location, 2. Multiply it by the standard error, 0.167, and then add the population mean of 3. So this becomes 0.334 plus 3. So 0.334 is 2 times 0.167 equals 3.334. So 3.334 equals the minimum evaluation. I'm just going to write in cursive. It seems to work better that way. Rating to convince the provost that training worked. So there's less than a 2.5% chance that you would get a mean in your sample of 3.334 or higher if the training did not work. So if you get a mean of 3.334 or higher, that means it's likely the training worked. Your sample no longer represents a possibility you could have gotten from the original population who didn't have the training, and it's probably worth your while implementing the training. Because there's only a 2.5% chance that you would have gotten something that high or higher due to a fluke if the training did not work. All right, one last example. You made it. So we're going to take a look at figuring out a specific sample mean, or in this case, range of sample means associated with a specific probability. So go ahead and take a minute to read this problem, and then we'll break it down. All right, so Theodore's trying to anticipate what kind of sample mean of download speeds would I get with any given 9 devices just due to chance. Really, he's looking at the middle 95% here. So let's break this down. Theodore is the owner of FlightPro, an app that provides maps and real-time weather reports for pilots. And he's not satisfied with the map download speeds on electronic devices. So right now, the mean download speed in the population is 90, with a standard deviation of 30. He hires a software developer to reprogram the map feature in FlightPro, hoping that now the download speeds will decrease. So he's really hoping that it kind of falls down here. Before enacting the update and testing it, he tests it with a sample of 9 devices. So he does the update on these 9 devices, and before he does it, he wants to anticipate the likely mean download speed, the middle 95%, that he would get in the sample if the update had no effect and results were just due to chance. So what is the range of expected mean download speeds that Theodore could expect in his sample due to random chance, even if the update had no effect? In other words, he wants to figure out what's the range of, if he took any given 9 devices now, right, from the original population, took those, looked at the mean download speed, what's kind of the major expected range of those mean download speeds in the original population. Then he'll kind of have an idea once he does the update on those 9 devices, really does it fall outside of that range of the realm of possibilities you would expect no matter what, even if the update had no effect. So let's break this down and look at it. First, we got to figure out the z for the high end and the z for the low end. Z low and z high. All right, so let's take a look at this. Middle 95%. Low end of that is here, right? High end of that is here. So the z-score for the low end is -2. The z-score for the high end is +2. Now we need to figure out our standard error before we can plug in all of our numbers to calculate those sample means. So our standard error is equal to the standard deviation of 30 divided by the square root of our sample size of 9. This becomes 30 divided by 3, which is a standard error of 10. So just due to random chance, for any given sample of 9 devices, he would expect the mean download speed to be about 10 seconds away from the original population mean of 90, or between 80 and 100, just due to chance. So if he did the update and he got a mean of 80, not impressed. It's really within the realm of possibilities. So now let's figure out, because he wants to really be picky here, he wants to expand it to the middle 95%, what would be the mean value on the low end? All right, so that's going to be our z-score of -2 times our standard error of 10 plus our original population mean of 90. This becomes -20 plus 90, which is equal to 70. There's our low end. X bar high equals +2 times 10 standard error plus population mean of 90 equals +20 plus 90 equals 110. So this would be 70. This would be 110. So if we look at this, if the mean download speed in the sample is between 70 and 110, Theodore should be unimpressed. There's a 95% chance you would have gotten that even if the update didn't work. If the mean download speed is 70 or lower, right, feeling good, he should be confident that the update worked because there's only a 2.5% chance of getting a mean download speed of 70 or lower if the update had no effect. All right. I hope these examples really helped. I hope it was worth your time. And I hope that now those problems in the lecture quiz are going to make a lot more sense than they would have if we just looked at the concepts and didn't do a ton of examples. I also hope that you're excited about the potential of using the empirical rule to make decisions in the business world. It is really useful. It's used quite a bit, especially in situations where you don't have access to the real data and you're trying to figure out if your assumptions make sense, if something worked, or just trying to figure out the characteristics of those in your population of employees or among all the items that you're dealing with in the workplace.